All right, since it's 6:04, I'll just go ahead and get started. So hello everyone, welcome to my virtual ISM final presentation night. And my name is Saujash, and this year in ISM, I studied aerospace engineering. So a big reason why I chose to study aerospace engineering is because humans in general, it is our nature to explore, be it our ancestors exploring continents or sailors crossing the Atlantic to the New World, or researchers today exploring the outer reaches of our solar system and even beyond. Uh, Aerospace engineering would be a great gateway for me to explore this field and and explore the urge to explore, essentially. So that's why, since this would be a gateway for me to get into that, I'm really interested in it as well. I chose to study aerospace engineering. So as I said, I'm Saujash Barman. I'm a junior this year, and I did ISM 1. And some of my other interests include physics, artificial intelligence, machine learning, etc. So this is a quote by my mom, actually, that I really strive to follow this year. Don't strive for success, pursue excellence. Success is just a byproduct of excellence. This quote really allowed me to focus on the task at hand, be it a research paper, a computer program, or even just a weekly blog post. Instead of distracting myself with the high expectations of a good result, I could focus on my task. So I would like to begin today by discussing the secondary research that I did in ISM. So this includes online courses, research papers, articles, and textbooks. So the first big research paper that I studied involved multi-objective evolutionary algorithms. And even though this may be a mouthful to say, it essentially just means having multiple objectives and writing an algorithm to optimize those objectives. For example, in aerospace engineering, there may be problems where we may need to optimize several parameters like a wing's lift, drag, structural length, and weight, and we may need to optimize them all at the same time. More objectives create more solutions, but in general, we don't want to converge into a single dominant optimization, even though that is a little counterintuitive. We want to uh, we want to design algorithms that can offer as many solutions as possible. One example of an MOEA, or multi-objective evolutionary algorithm, is non-dominated sorting genetic algorithm, or NSGA. The next portion of my first semester research involved a little bit more of material science aspect of aerospace engineering, and it was about advanced aluminum matrix composites. And these things are essentially just materials which have an aluminum base with pores in them that are filled with silicon carbide. And by conducting various tests, it has been seen that this matrix composite of aluminum and silicon carbide may actually be a better fit for aerospace, for use in aerospace context. And this paper kind of taught me the difference between an alloy and a composite, which is also pretty important. And it gave me a slight introduction to the material science aspect of aerospace. After that, I started getting into rocket propulsion, and I read it. It was kind of a textbook, and it gave me an introduction to not only rocket propulsion, but it taught me the difference between rocket propulsion and jet propulsion, and the principles behind the acceleration of jets and rockets, and what the differences between different types of rocket engines are, like turbojets, ramjets, and scramjets. So that was a synopsis of my secondary research. But in addition to my secondary research, I also conducted some primary research, and these primarily consisted of informational interviews with college students and professionals in the industry. So these were all the professionals I interviewed, and as you can see, they range from college students to college graduates to systems engineers to even pilots and service engineers. And I also met both of my mentors through this process of conducting informational interviews. Mr. Kevin Kobilka, who is present with us today, is a NASA Pathway Scholar and an RPI PhD student and researcher at the Sensing, Estimation, and Automation Lab, or SEAL. Captain Scott is currently a professor at Florida Institute of Technology, and he's also a former NASA astronaut who flew to space in two space shuttle missions, the STS-72 and the STS-87, and he was a mission specialist in both of those. I'm really grateful to be mentored by both of them, and further into the presentation, I'm going to be talking about what is the product I created under both of their mentorship. Before starting a mentorship, though, by the end of the first semester, I created something called the original work. And there's another QR code here, and this will also be present in quite a few slides from now. And this is essentially the report that I created for my original work. And this was my own DIY model rocket project. All right. So the basics of rocket propulsion and history of rocketry is what I started looking into first when I created my original work. So rocket propulsion is heavily based on Newton's three fundamental laws of motion. And we know that throughout history, rockets have largely been used for militaristic purposes. And what really accelerated advance in spaceflight and rocketry technology in the United States was the space race, which happened between the Soviet Union and the United States during the Cold War era. All right, so here we can see a diagram to the left and an equation to the right. This gives us a very basic overview of what rocket propulsion is about. On the diagram, we can see we have a mass delta M that is leaving the rocket, and that is essentially the fuel, which is exerting a force in the downward direction. And according to Newton's third law, that also generates a reaction force in the upward direction, which propels the rocket upward. And we also have a free body diagram of the rocket, and we can see that the force that is generated, the propulsion force that is generated, is actually greater than the weight. So it counteracts the weight and causes an acceleration of the rocket upwards. We also have an equation. This is called the general thrust equation, and it says the net force on the rocket is m dot v minus m dot v. So that is a statement of essentially change in momentum. M dot represents the change in mass with respect to the time. Usually in classical mechanics, we always look at momentum in scenarios where our velocity is changing with respect to time and mass stays constant. But in the case of a rocket, the mass actually does not stay constant, since we can see the delta M is, there's constantly a mass delta M leaving the rocket as it propels upward. This third term right here, the P times the difference in P times A, is to account for the differences in pressure that occur as the rocket moves or ascends through the atmosphere. As the rocket's elevation increases, the atmospheric pressure on it decreases, and it does cause a net force on the rocket. So coming to my actual original work, it was a model rocket. A model rocket is created using non-metallic materials, and it's built for relatively low altitudes and quick recovery. To the right, we can see the parts of a basic model rocket. Rocket cannot have all of these. Like mine did not have number 8, an altimeter, and number 9, payload bay. But in general, most of these parts will be present in a model rocket. A fascinating part of the model rocket is its engine. So I would like to spend a little bit of time talking about it. in the diagram, number 1, the nozzle, is a crucial part of a model rocket engine. It delivers large amounts of kinetic energy into the system by squeezing gases into a tiny tube. So it follows the principle of conservation of flow rate, and in and using that, it can deliver large amounts of kinetic energy into the system. Number 2 is just the motor case that encloses all the contents of the engine. The number 3, the orange portion, is actual propellant. In lower class model rocket engines, so the rocket engines are labeled alphabetically labeled from A, B, C, D, and so on, where B is twice as powerful as A and C is twice as powerful as B, and so on. So from around A through F, the model rocket engines are powered by black powder. But as we get into more powerful model rocket engines, ammonium perchlorate is used as the propellant. The number 4, the green portion, is the delay charge. And the delay charge is essentially there to have a gap between the ejection charge, which I'll talk about later, and the propellant. This is there to ensure that the parachute of the rocket does not deploy immediately after the propellant runs out, because in that case, the parachute would deploy when the rocket is on its way up, and we don't really want that. We want the rocket to run out of propellant and then and then we want some downtime of a few seconds for the rocket to hit its apogee or its highest point, and then possibly a little bit on its way down even. We want the ejection charge, which is actually number 5, and it's almost a mini explosion within the rocket, and that is what causes the parachute to deploy. And then we get to number 6, which is the top cap enclosing all of the contents of the engine. Creating a model rocket it takes up a lot of time and resources, but there is no guarantee that it will be correct. It will be the first time you build it. So RockSim is actually a software that we can use to design a rocket virtually and test it, so that we can save time and resources and already make the necessary changes that we need to our rocket before even building it. And when we do build it, there is a higher chance that the launch goes as we plan it to go. So these are a few pictures of the interface of RockSim. As you can see, right here is when I was designing my rocket and changing some of its parameters. And the top left picture is the simulation window. We can see we can launch a rocket, and then it collects a bunch of data for us into a table, and we can analyze that table and make changes accordingly. All right. Oh, I guess I need to. Oh, I have that. Okay. So here's a quick launch video. Disclaimer: all did not go as planned, but it's fine. Nothing burned. Everything was okay. It was a great learning experience. But I'm just going to share a quick snippet of the launch. And the audio quality is also a little poor, so I apologize for that. Let me make sure I share computer sound. All right.
Okay, Saujash has the orange rocket on the mid-power pad with a D motor in it. Starting countdown. 5, 4, 3, 2, 1, launch. And the shock cord broke. Heads up out in the field. Yep.
So I don't know if you could hear the exclamations in the background when the rocket was in the midair. What happened was the shock cord, which is the cord that connects the rocket to the parachute, it broke. And even though my parachute deployed, it was just flying on its own, and my rocket just crash landed. There was the rocket did not sustain too much damage, but I definitely learned I need to use a stronger shock cord, and it was just a great experience in general, even though everything was not perfect. Oh no, I don't want that again. Okay. All right, so let me get into the final product portion now. This is the portion that I worked on with both of my mentors, Captain Scott and Mr. Kobylka. There were two parts to it that I worked with both of my mentors, and let's head into part one. Again, you can scan this QR code right here, where you can find the report that I created that was associated with this part of the project. And the part that I worked on with Kevin was about orbit determination using only terrain images from an onboard camera. So in this problem scenario, we're assuming that we have an object orbiting another planet, and we're assuming we have a camera on that object, which can take images of the surface beneath it. What we want to do is estimate the orbit of the object just based on those images. And also we are assuming we have some knowledge of the terrain of the surface, and we know the positions of certain landmarks which are captured within the image when the image is taken. There's also a theoretical way to calculate the orbit or figure out what the orbit could be using something called the two-body problem, which I'll talk about in a couple of slides. But I decided to take a more realistic approach in this case, and what would happen in a real world scenario when all the data we really have is just pictures and some knowledge of the terrain. This QR code will be in future slides as well, so you can scan it anytime. All right, the abstract of this project would be to explore a pre-existing method of satellite orbit determination that collects live images of terrain, like I said, from an onboard camera, and it marks known landmarks on them and uses that information to generate position and velocity measurements for the satellite, which would allow us to estimate the orbit of the satellite at a later time. So before we actually get into how to solve the problem, let's discuss the two-body problem, which is drawn out in this diagram on the left. You can see we have the Earth and a hypothetical satellite orbiting the Earth. What we do is equate the force of, we use the law of universal gravitation and equate that to the centripetal force exerted on the satellite. We can do some algebra, and just basic physics will tell us that the velocity of the satellite is going to be equal to the square root, and it's going to be dependent on the gravitational constant g, a constant mass of the planet, capital M, and the distance between the center of the planet and the satellite, r. We can determine the velocity this way, but like I said, this is a theoretical way of doing it, and all we really have is pictures. So let's use those pictures and our terrain knowledge to figure out the orbit. And what I would like to mention is the two-body problem doesn't only have circular orbits. It consists of elliptical orbits as well. But this special case is used in this case because the calculations are much easier with a circular orbit. And when we actually figure out the velocity of our satellite or our hypothetical object using the method I'm going to talk about in the next few slides, we can actually verify it with this simple formula. So to be able to verify the accuracy of our method, we use a circular orbit instead of using a complicated math for an elliptical orbit. But it does work for non-circular orbits as well. All right. The first step that we need to do is called the direct linear transform. And what we need to understand about the direct linear transform is really just this diagram that we have here on the left. The blue part is our planet, and there is a satellite orbiting that planet. The red box right here is what is called the field of view of the camera that is aboard the satellite. That is essentially the maximum amount of surface that we can view through our camera. Within that field of view, we have these three dots, which are what we are calling the known landmarks. Now, these arrows pointing from the satellite to this landmark, to these three landmarks, are called the line of sight vectors. So these arrows are called vectors, and the arrows specifically pointing from the satellite to the landmark are called the line of sight vectors. The arrow pointing from the center of the planet to the satellite is the R vector, or that is our position vector. And our known positions are P vectors. So we have three P vectors in this case. And what is worth noting is with the direct linear transform, it's essentially a mathematical technique we are using to estimate the position of this satellite relative to these landmarks. And in this simulation, we actually need to calculate our line of sight vectors. But in the real world, and we need to calculate our line of sight vectors because we do not have actual live images in this simulation. We're just assuming we can have images and this is how we would do it, but we do not actually have those images. So if we did have the images, we can collect the line of sight vectors and estimate our position vector. But in this case, in the simulation, we'll have to assume a known position, which is the R vector, and then calculate line of sight vectors. And using those line of sight vectors, we can then return a position vector value, which we can check if it was correct with our original position value that we assigned. So the process is the same for the simulation and the real world. It's still a direct linear transform. It's just we have to do it a little differently since we are in a simulation and we do not have actual data. On the right is just the MATLAB script that I wrote to carry out this direct linear transform. We create a linear model, just vectors, and these L1, L2, L3, L4 are 4 line of sight vectors. We stack them onto a matrix, and we are using something called a cross matrix. We do on each of those line of sight vectors, we stack them onto another matrix, which is the H matrix, and using that H matrix, we can create a linear model that gives us our estimated R value. So that is our estimated position for our satellite. Next, we'll move on to the Gibbs method of orbit determination. Now, we have the direct linear transform from the previous slide, which gives us our position estimations. And what we're doing with Gibbs is estimating our position 3 times in three different points in time, which we're going to call T0, T1, and T2. Once we generate 3 position vectors in these 3 different times, we can use Gibbs method of orbit determination, which is a basic technique in orbital mechanics to calculate the velocity of our object at this middle time right here. So we need 3 position vectors to give us our velocity for the middle time. And that is exactly what we are looking for. Because if you remember in the 2-body problem, what we solved for was velocity. And when I said it's dependent on the constants and our radius. So that is exactly what we want. It's the velocity. And again, we had the MATLAB script for carrying out the Gibbs method of orbit determination. And it's just a lot of normalization of vectors, using cross products, checking if the vectors are coplanar, and then plugging in into the appropriate formula to get our final value V2, which will be the velocity that I spoke about. Again, we need to remember though, we are still not done because this is a simulation And like I said, we do not have live images. So what we need to do is simulate the landmarks. We are assuming we have this satellite on top of this planet surface, and over here, to make the trigonometry easier, I said that the curvature is negligible. And first we need to calculate the field of view of the satellite, which is what is the maximum amount the satellite can see. So that depends on the angle the camera can rotate itself. So using this figure, we can see it's some basic trigonometry which will allow us to determine this distance x, and that's half of the side length of the field of one side of the field of view. So if we assume our field of view to be a square, x is 1/2 of one of those sides of the square. So once we calculate x, we can figure out what our entire field of view is. And on the right, we can see exactly that. It's a MATLAB plot, which is a square field of view. And in that square field of view, we have random points generated, which represent our landmarks. Now, in this case, we have generated way more landmarks than we need, but this is just for demonstration. So these red points are random values generated within the interval of this field of view. So now we carry out that same process, but we need to do it 3 times, because once we generate a cluster of landmarks, we can estimate our position once using direct linear transform. But we need to do it 3 times so that we can generate 3 position estimates and carry out Gibbs method. So we do that by using something called the direction cosine matrix. And the idea here is we have a set of landmarks, and we're going to generate a new set of landmarks and rotate it by a set amount, which is a theta in this matrix. So this first one right here, you can see there is this cluster on the top, and then we generate a new set and multiply it by the matrix to rotate that set by 30 degrees or however much we want. And we generate a new set again and rotate it by 2 times 30 degrees, which would be 60 degrees, to generate a third set. Now we have 3 clusters of landmarks, and we can do our position estimation, apply Gibbs method, calculate our velocity, and that is how we determine our orbit. So again, remembering in this case, our orbit is circular, but it also works for non-circular orbits. So this is the experimental way of determining orbits using limited available data. And this method can, like I said, determine non-circular orbits as well. And in fact, most orbits in the real world are not perfectly circular. Personally, I gained a lot from this project by familiarizing myself with new linear algebra techniques and the MATLAB programming language, which I did not know before. All right. Now we're going to move into part 2 of the project. And this is the part I worked with Captain Scott. And this is taking a deeper look into NASA's space shuttle program. I wanted to capitalize on Captain Scott's invaluable firsthand experience on an actual space shuttle mission. Hence, I also took a dive into the ISM procedures, which are the procedures when the space shuttle ascends through the atmosphere into low Earth orbit. And again, there's the QR code right here, which you can scan. It's going to be on future slides, as usual. And you'll be able to view the report that I created associated with this part of the project. So before I talk about the ISM procedures and about the rocket itself, let me give you a little bit of context for the rise of American spaceflight, which was, like I said before, primarily fueled by the space race during the Cold War era. In 1958, NASA was founded, and soon Alan Shepard became the first American man in space in a Mercury mission. The Mercury was soon followed by Gemini, and Gemini was a prep program essentially for the larger Apollo mission, which we know, of course, took the first man to the moon, and many people after that as well. And the space shuttle came after Apollo. It ran from 1981 to 2011. And the shuttle rocket is pretty unique. It has 3 parts: an external tank, which carries liquid hydrogen and liquid oxygen fuel, 2 solid rocket boosters, which are the primary ways that which is the primary kind of engine or the primary propelling force for the first 2 minutes of the rocket as it ascends through the atmosphere for the first 2 minutes of the flight. It has like the name implies, it has a solid propellant. And at the back, we have a delta-winged plane-like orbiter attached to the fuel tank. And this is where the crew resides and all the missions are carried out. Each shuttle mission could carry up to 8 astronauts and 50,000 pounds of payload into low Earth orbit. A defining characteristic of the shuttle was its use of solid propellant in its solid rocket boosters. The use of aluminum powder as fuel and ammonium perchlorate, which, if you remember, is also a propellant for model rocket engines, but at, of course, a much smaller scale. So the ammonium perchlorate is the oxidizer, and the aluminum powder is the fuel. And it was the first of its kind, and it generated about 83% of the thrust of the entire vehicle up until it reached low Earth orbit. After which, the boosters were jettisoned off and parachuted into the ocean. This is the cool part. And they were later recovered, examined, refurbished, and again reused. So that is the and even the orbiter was reused. So the reusability of the space shuttle rocket was a very unique aspect. All right. So before beginning our discussion of the different ascent procedures and abort modes, the engineering of the solid rocket booster is worth noting. The SRBs are actually kind of rockets themselves, and they are fueled by solid propellants. And solid propellants are really gain traction because of the high amounts of power that they're able to deliver with the same amount of fuel as compared with the liquid propellant. The two boosters carry the entire weight of the external tank in the orbiter and exerted about 2.8 million pounds of force to get the vehicle up to an altitude of 15,000 feet in a mere 2 minutes. The solid rocket boosters were 69% of the total liftoff mass of the vehicle, so it was a significant portion of the mass as well. One of the most interesting parts of the solid rocket booster for me are the thrust vector controlling systems, which is the TVC, which you can see in the back in kind of this orange color. These are essentially components of the rocket that are integral to the fine-tuning of its trajectory. So it's not just propellant leaving the booster. There are vector controlling systems that fine-tune the trajectory of the solid rocket booster. It allows the rocket to roll in the appropriate direction once it leaves the launch pad and constantly adjust the rocket's path throughout its trajectory. In technical jargon, you could say that the TVC systems have hydraulic gimbal servo actuators, and that's, again, a mouthful to say, but they are just referring to the fact that the motors on the solid rocket booster swivel or gimbal and are powered by fluids, or they're hydraulic. The swiveling is how the attitude and trajectory of the vehicle is fine-tuned in the 3 dimensions called roll, pitch, and yaw. All right, let's discuss the ascent profile of the solid rocket booster, or not the solid rocket booster, of the space shuttle. We can the diagram here really is what's called the nominal ascent profile of the vehicle. And in aerospace engineering, the term nominal is used to describe something that is within the acceptable limits, or ideal, or more like ideal enough to not abort. A few key things to note about this diagram are the solid rocket booster separation point, the MECO, which stands for main engine cutoff, and that is a major milestone in the ascent profile of the shuttle. And soon after MECO, the external tank, which was the big orange tank, it separates off to eject irrelevant or not required mass. And then the OMS 2 maneuver is carried out, and then further in-orbit procedures are carried out, which is beyond the scope of my research. So the ascent procedures on the shuttle are actually are pretty complicated, and I you can see the difference in the left and the right pictures is the blank document and the one I annotated on. It took me a lot of notes to parse all of this and all of what this means, and it has a lot of abbreviations and a lot of technical jargon that really wouldn't make sense to a first timer at all. So going over this very briefly and giving a brief overview. So what we are looking at right here is these kind of square root kind of symbols. They're essentially check marks. So when we see SRB SEP and a check mark next to it, it is an indication to check the solid rocket booster separation. And if it does not work, there is a backup auto separation at 2 minutes and 21 seconds into flight. And that happens when the chamber pressure is less than 50%, and then 5 seconds after that. And the MECO time is then checked. And if it is not stable, so the important thing about this checklist is it not only tells the crew what to do when everything goes right, but it gives a whole plan for every single step that needs to be taken when anything can go wrong. So throughout this page, we can see many uses of the word if. So if this goes wrong, then do that. If this goes wrong, then do that. If not, then you can skip down to this bottom portion. So when we're going to check at around 3 minutes. All right, so at around 3 minutes, we're going to see if we need to abort, if there's conditions that would require the crew to abort the mission. And that only occurs when the MECO target, which is, if you remember, is the main engine cutoff target, is not met. So when there's a what's called the MECO underspeed, so the rocket is not fast enough to get into orbit, or it's not in the correct height or in the correct location. So that is when an abort would be required. So RTLS stands for return to launch site. TAL stands for transoceanic Atlantic abort. And those are two aborts that would be needed to carry out at this moment in time. Going through, okay, at 13.2 thousand, when our speed is at 13.2 thousand, we check our roll, and if one of the engine malfunctions, we have to the crew has to go to manual throttle with 3 engines, and after that do the manual shutdown at 25,700 feet. If in the unlikely case the rocket needs to function on 1 engine, then the single engine roll control needs to be checked to be on, and the main propulsion system, when the main propulsion system has 5% propellant, we need to go into manual throttle, and when it has 2% propellant left, we need to go into minimum throttle and then auto throttle. So, and then we get to the big milestone, MECO. And in this case, this is the STS-134 mission, and the MECO occurs at 25,819. I believe this is feet per second. I might need to be checked on the units, but that is the speed target, and everything happens before that. So all the aborts that need to be, if there is an abort required, it needs to be taken care of before MECO, and everything kind of builds up to the big MECO target. And soon after MECO, we do the external tank separation, and we have further instructions for the crew on what to do if the separation is inhibited or it needs to be done manually, how to dump the propellant, how to carry out the propellant dump sequence, and just things like that. So it goes on, and then by the end of it, we go to the next maneuver, which is the OMS 1 maneuver, and our ascent is complete. So that is kind of a synopsis of the ascent procedures that I looked into. And next, let's talk about I believe we were talking about the abort modes. after this. And right. Yeah, so the ATO abort mode is abort to orbit, and it's an intact abort mode designed to achieve a temporary orbit which is lower than the actual nominal orbit. And it requires less performance and allows time to evaluate problems and then choose either an early deorbit burn or an Ohm's maneuver to raise the orbit and continue the mission. So it's kind of buying time, essentially, if you want to think about it that way. The AOA, which is the abort once around, it is performed when orbit cannot be achieved and maintained. This abort mode is designed to use the existing performance to make a revolution of the Earth and then land at a base. It could be Kennedy or another base like Edwards Air Force Base, or just but we make a revolution around the Earth and then land. There are two types of AOA trajectories: the AOA steep and the AOA shallow. And the steep one looks like, essentially just looks like what the end of mission return path would look like. But the shallow one is a little different. It's like the name implies, it's a shallow landing. The TAL is transoceanic abort landing, and as you can see in this diagram, it kind of launches from the launch site and then something goes wrong and you land across the ocean. So you land in a base in Europe across the Atlantic. And the RTLS is just the return to launch site. So when something goes wrong, you come back to the launch site. So that was the scope of my research in both of these sections. And in the QR code, you can see my final product for both of these components as well. And that actually brings us to the end of my presentation. And I would before I stop, I would really like to thank my ISM teacher, Ms. Secord, who is actually unfortunately not with us today, but she really helped me get kind of rolling, with my research and with my interviews at the beginning of the year, and she really supported me throughout this ISM year. And then I would like to, of course, thank both my mentors, Kevin and Captain Scott. Every time I met with both of you, I learned something new, and it was great talking to you and learning from you and creating this whole product. And finally, my parents, who are also here. I think I got disconnected. I don't know till what part you could hear me, but okay, cool. That sounds good. Let me. That was the last slide anyway, so I don't need to share it again. But yeah, like I was saying, I'd really like to thank my teacher, Miss Secord, my mentors, Captain Scott and Kevin, both of them. They really helped me build a great product, and I learned a lot from them every time I met with them. And it was just a great experience this entire year, doing all the research, building my own rocket, doing the research on this orbital mechanics and orbit determination stuff, and then also looking into the space shuttle ascent procedures. It was just a great experience overall. I look forward to doing it again next year. And yeah, before closing out today, maybe Kevin, if you could speak a few words, and then Captain Scott as well.
Sure. Can you hear me?
Yes.
I just want to say you did an astounding job, and the stuff you worked on with the direct linear transform is used in actual spacecraft GNC applications. And the fact that you were able to put together something that could be a useful part of a real spacecraft GNC software, and that is sort of with all the heavy linear algebra and formulas and everything you had to figure out, especially with getting it to work in MATLAB, which you didn't have much experience for, is really, really impressive. And you should be really, really proud. It's a really nice piece of work you did. Congratulations.
Thank you. Captain Scott, would you like to?
Absolutely, and thank you so much. I think you did an outstanding job as well. You took a very, very, very complex set of procedures and systems and condensed it down to something that a non-aerospace professional can understand. So you do a very, very good job. I'm very, very pleased and very proud to have worked with you. I know your future is very bright. I have nothing but high hopes and high expectations for you. So keep up the good work, and I'm sure I'll see you down at NASA here one of these days, either as an astronaut or an engineer or scientist, or all of the above. But good luck to you, and thank you so much.
That is the dream. That would be a dream come true. We will see what happens, but that would definitely be a dream come true. With the help of
So
mentors like you.
when does your teacher see the presentation?
Well, I am recording this, so she would be able to view it when I submit the recording to her, which would be tomorrow or maybe day after.
Okay.
So yeah, pretty soon.
I'm sure she'll be pleased.
I hope so too. Right. So thank you, Mr. Inhouse. Thank you, Mr. Murray. All right. So yeah, that brings us to the end of this. I did go a little over time. Sorry about that, but yes. Thank you everyone for joining. It was great presenting my work to all of you. I hope you liked it, and see you guys soon.
All right. Take care and be safe now. Bye-bye.
Good job, Saujash.
Good job again.
Good job.
Thank you. Thank you. Bye-bye.
Bye-bye.